In this section, I would like to discuss about multiple chirality centers and how we come up with R and S assignment to these stereoisomers. So I'll go over one of the homework problems that I have assigned, and that's number 12, part A. So let me first draw this. This is 6.12, chapter 6, number 12. So you have a carbon and a carbon. So there are two carbon, and there'd be hydrogen projected towards you, methyl group towards you. So let's write down this hydrogen, the methyl group is projected towards you. Then bromine away from you. Now on the second carbon, there is one hydrogen projected towards you. Then OH group, again with thick lines, projected towards you. And there is a dashed line away from you, which is CH3 or methyl group. Let me check whether I copied the question right. It's always a good idea. If you have molecular model, I suggest that you build it. That way you'd find that you'd be right every time. Now there are two chirality centers. You remember the definition of chirality center? That's the center, like in this case, let me use a different pen. This is one of the chirality center. We have four different groups bonded. So Br is one of them. Methyl group is another one. Hydrogen is another one. And the rest of these molecule would be the other one. So these are the four groups. So if you have a model, you can use four different colors. Normally we use hydrogen for as white color for hydrogen, and other colors for other elements or different groups. Now question is, how do I get R or S? Now the problem is very similar to just one chiral center problem where we assigned priorities. Let's do that. Br having the highest atomic number gets the highest priority, so this gets 1. The next priority would be obviously the big group at the bottom. Why? Because carbon is directly bonded, so it could be methyl or the big group underneath. In both cases of carbon, so you can't make a decision based on the first attached atom. So you need to look for the next atom with higher atomic number. So that's the big group has. It is bonded to oxygen, whereas in methyl group, they are all hydrogens. So obviously, priority 2 is the one with big group with CHOH, CH3. So methyl group gets number 3, and hydrogen obviously gets number 4, lowest priority group. Now there, again, if you make a model, it'll be quite simple for you. You hold the model in such a way that hydrogen is completely away from you. And then you hold on to number 1 priority atom, which is Br, and move your hand from 1 to 2 to 3. And imagine that's the steering wheel of your car. Now if your car is making a right turn, that's R. If it's making a left turn, that would be an S. So in this case, let's see what we got. So 1 to 2 to 3, I get right turn. So that means first steric, this chirality center gets R. Now keep in mind, each chirality center has to be R or S if there is no plane of symmetry. And in this molecule, there is no plane of symmetry. Now let's examine the second chirality center. Now either we can redraw this molecule so that not to mess up this whole thing. So I think let's do it, redraw it, because otherwise when you're learning for the first time it could be confused. So let's redraw the whole thing. So hopefully it did not take too much longer. You would have Br just like what we have drawn before. This is CH3, and then you have another carbon with hydrogen, and then a thick OH group towards you, methyl group away from you. This time we are focusing our attention on the second chiral center. Again, why is this a chiral center? Because there are 4 different groups bonded around that center. OH is one of them. Methyl group is the second one. This whole big thing is the third one. And hydrogen is the fourth one. Let's now assign priorities. It's the same molecule I've drawn for clarity so that I don't mess up in assigning R or S. So again, priority 1 goes with OH group because oxygen has the highest atomic number. Comparing all those atoms directly bonded to this chiral center where I have shown with an asterisk. So this gets number 1. So the big group gets number 2. I hope you understand that, why big group gets number 2. Because methyl and this big group both are directly bonded to carbon, but then that means you can't make a decision based on the first bonded carbon atom. So you need to look for the next bonded atom, which is Br or another carbon. But methyl group has all hydrogen. So that's why this big group gets number 2, methyl gets number 3, and hydrogen gets number 4. Now let's figure out this. You should be placed this molecule in such a way that the hydrogen, number 4, is farthest away from you. So your eyes would be here, and hold on to the highest priority group, which is OH, and go from 1 to 2 to 3. And you'd find that this is also right turn. So this configuration is also going to be R. So our answer is both the chirality centers would have R configuration. So I'm hoping that you understood this. When there is one chirality center, there will be 2 stereoisomers, which are mirror images of each other. And we discussed that in previous section. On the other hand, if there are 2 chirality centers, there will be 4 isomers, provided there is no plane of symmetry. And I'm going to show you with a model that how 2 chirality centers can give you 4 or fewer than 4, depending upon plane of symmetry. If there is no plane of symmetry, n chirality centers would give 2 to the power n number of isomers. And some of those would be enantiomers when they're mirror images of each other. In this slide, we're going to discuss what meso compound is for more than one chirality center and what diastereoisomer is. So I made a model here with 2 chirality centers. You can see here there's 2 chirality centers, and you can see like this. There are 2 chirality centers. Carbon, around each carbon there are 4 different groups bonded. So that makes it 2 chirality center. Now, if you look at this molecule carefully, this molecule also has a plane of symmetry, even though it has 2 chirality center. And this is the plane of symmetry. I can cut it into 2 equal halves. Let me hold it this way so that you can better see it. I can cut it into 2 halves. You can see that 2 halves are identical. In the same way, when you make the model, you can see for yourself that 1 half is identical to the other half. Of course, you need to make the right orientation. Like in this case, if I may have an orientation like this, then it may not appear that you have 1 half same as the other half. So what you need to do is rotate, try to bring those two groups like one behind the other. This would be possible only in those cases where there is a plane of symmetry. So in this case, there is a plane of symmetry. What that means is, in this case, its mirror image is not going to be a new molecule and is going to be the same molecule. Let me show you by building both. And you can see here, let's hold them side by side like this. And you can see that one is the mirror image of the other. Imagine there is a mirror in between them. So red is reflected to red on the other side. Similarly, all these atoms are reflected to each other. Now the question is, even though they're mirror images, but truly they're not new molecules because there's a plane of symmetry, and we can see for ourselves that it's not a new molecule. So let's make that change in orientation and try to superimpose them. If I can completely superimpose them, that means it's the same molecule. As you can see here, I completely superimpose them. I hope you can see it in right orient. So I completely superimpose them. That means they represent identical molecules. Even though they are mirror images, they are not new molecules. Now I also made another structure where you'd find that it'd be a distinctly different compound. So let me grab that. Again, keeping the group same. Two chirality center. They're also now mirror images of each other. You can see that these are two chirality center. They look the same as the other ones that I've shown you, but truly they're not identical. These two are mirror images and there is no plane of symmetry. That means no matter how you rotate this group, under no situation you'd be able to discover a plane of symmetry that would split this molecule into two identical halves. So obviously these two are then distinctly different molecules. Let's test this by trying to superimpose them. My red is oriented together, so let's try this. Bringing those two reds on the same side, two reds on the same side. But look at this, other groups are not matching. So that means these represents distinctly different isomers. They're mirror images, so they're enantiomers. Now another definition that I wanted to give you is called diastereomer. Remember the meso isomer that, let me brought it in here. They are not mirror images. This meso and the one that I just built, which doesn't have a plane of symmetry, they are not mirror images, but they're isomers, and they are called diastereomers. So keep this in mind. Even though there are two chirality centers, here we have three isomers. We're supposed to have four if we had no plane of symmetry. But in this case we have three because there is a plane of symmetry. In this slide we're showing you examples of enantiomers and diastereomers. And I would like to explain to you how this kind of labeling was done. If I just focus on one of these molecules once, for example, I can number it as 1 because that carries the functional group COOH. This is 2, this is 3, and this is 4. So when it says 2R, 3R, that means the second location around that chirality center, the configuration is going to be R. So that's what 2 means, is the location and the longest chain. 3R means in the third location also, if you try to find out configuration around the third location, is also going to be R. If you take the mirror image and if you look at each of these carbon and its configuration, you get 2s and 3s. So in other words, in reflection, R becomes S and S becomes R. In the third case, you can see the third case is not a mirror image of 1 or 2, and that's a diastereomer. So its mirror image is enantiomer. There is no plane of symmetry in any of these molecules. So you get distinctly 4 different isomers as we expected, because there are 2 chirality centers. You get 4 when there is no plane of symmetry. In this slide, you're looking at possible isomers for tartaric acid having 2 chiral centers. Now let me show you. This is one chiral center, this is the other one, shown with small number 1, 2, 3, and 4 that's for the longest chain, and 2 and 3 represent chiral center, because around 2 you'd see 4 different groups bonded, around 3 you'd also see 4 different groups bonded, and that's why 2 and 3, the small number 2 and 3, represent 2 chiral centers, and that's the case in each of these structures that I have shown you. Structure 1, I'm talking about now bold-faced 1 and 2 are mirror images of each other. So obviously they represent enantiomers. But before we label them as enantiomers, we have to make sure that there is no plane of symmetry existing. If you examine this, you'd find that there is no plane of symmetry in either of these two. So mirror image is going to be a different molecule. Now, around small number 2, I'm talking about this carbon, configuration is R. So we call it 2R. 2 is the position of the carbon, and 3R is the position of the second chiral center. And that's also R. But in the image, mirror image, around 2, if you examine, you'd find that it's S. And around carbon 3, it is also S. So in the second carbon is 2S, third carbon is 3S. 3 represents the location of that chiral center. So what we learn here is when you take a mirror image of 2R, 3R, that gets changed into 2S and 3S. If you're now looking at molecule 3 and 4, I'm talking about the bold-faced number 3 and 4, on the screen they look like mirror images of each other, and they are indeed mirror images of each other. However, you'll see a plane of symmetry because I'm drawing it at this orientation. You can clearly see that one half is identical to the other half. I've shown you in the video clip that whenever you discover a plane of symmetry, those molecules would not have mirror image different from themselves. So in other words, mirror image would be the same molecule as what you're seeing on the left hand side. So in other words, this molecule and this molecule 3 and 4 represent the same molecule. So whenever you have this formula, you'd expect 3 different structures, and one of them is meso, the right hand side compound. 3 or 4 would be a meso compound. So what's the meso compound? These kind of compounds have chiral centers. In this case, you have these carbons, chiral centers, having 4 different groups bonded, but they also have a plane of symmetry, and that's why it's meso compound. Now I'm going to do one of the homework problems, which is 6.17, and it's on page 206. So it's a good idea to always read the question carefully before you do the problem. So it says that which of the following structures represent meso compounds. So let me draw that, and I'm going to do A, 17A. So I'm going to do 17A. So let me write down first. It's a 5-membered ring. So let's draw a 5-membered ring. So that 5-membered ring with OH, with thick line projected towards you, and then hydrogen with dashed line or dotted line, is behind you, and then the other OH, the next carbon, is also projected towards you, and its hydrogen is away from you. So this is what is shown, and then now the question is there any plane of symmetry here? With this orientation, you see that yes, there is a plane of symmetry. That's the plane of symmetry, and that splits this molecule in identical halves because two OHs are on the same side, two hydrogens are, even though it's away from you, but they're on the same side. So you can split it into identical halves, and that's why this would represent a meso compound. So let's write down here, it's a meso compound. In the same way, you can try the other ones and see for yourself whether they are meso or not. Sometimes you need to rotate the molecule, like part C. Now, in problem number 18, so let's try one from problem 18. So 6.18, this is a word problem. Which of the following substances have meso forms? That means they're recognizing that you may have more than one form. 2,3 dibromobutane. So 2,3 dibromobutane. Of course, since it's butane, so first write down four-membered carbon, methane, ethane, propane, butane without the hydrogen. Now 2,3-dibromo. That means there are two bromo groups. One is in location 2. You can write down numbers like this: 1, 2, 3, 4. So 2 has one bromo group. The 3 has the other bromo group. Now I intentionally wrote down like this so that you can see clearly that there is a form where you can have a plane of symmetry cutting it into two identical halves. And this form that I'm showing you would have a plane of symmetry, and in other words, it's a meso compound. So one of the forms has a meso isomer. Even though I defined this before, I want to remind you again that whenever you have a 50-50 mixture of two enantiomers, it's called racemic mixture. And you remember enantiomers, these are non-superimposable mirror images of each other. Now one rotates planar polarized light by, say, +10, the other one is going to rotate by -10, especially the mirror image one. So racemic mixture would have 0-degree angle of rotation. So in this aspect, it would behave like as if there is a meso compound in your system. Now separation of this kind of molecules, I mean enantiomers, is much harder because they have same solubility, melting point, boiling point. So basically you need to find a chiral molecule that would react with both, and then you can separate them as diastereomer. If a chiral molecule attaches, if the same chiral molecule attaches to both these enantiomers, then you're not going to have enantiomers anymore. You are going to get two diastereomer, and that's how you can separate them. Now here we are showing you all these definitions of isomers. Constitutional isomer, and for example butane and 2-methylpropane. Let me remind you by drawing a skeleton structure of butane. 1, 2, 3, 4, that's butane. And then you can have 1, 2, 3, and 2-methylpropane, the 2-methyl here. Both have same formula, but they're not the same structure, they're not the same molecules. They're structurally different. Connectivity is different. And that's why they're called constitutional isomers. On the other hand, stereoisomers, they have the same connectivity. So just by looking at it, you may not be able to tell whether those are identical or not, because I mentioned to you, either you try to discover a plane of symmetry or you try to get the mirror image and see whether they represent the same molecule or not. Now stereoisomers are of course like this. You'd be subdivided into diastereomer or enantiomer when they're non-superimposable mirror images. Diastereomers are not mirror images of each other. Cis strands are also diastereomers, but when you have chiral centers, they'll be chiral diastereomers. Whenever you have multiple stereocenters or chiral centers, obviously you can have a number of isomers.